When the mast is tilted in directional flight, the damper assembly is tilted with it. Since the stabilizer bar tends to remain in its same plane of rotation, the dampers immediately exert pressure on the bar, causing it to realign itself with the mast in 3 to 5 seconds. Since any disturbance affecting the rotor or fuselage would rarely last more than a few seconds, we suffer no effective loss of stability, and the dampers give the pilot greatly increased control. The stabilizer bar, then, because of its gyroscopic property of rigidity in space, is able to modulate sudden changes in attitude of either the rotor or fuselage. With the aid of the hydraulic dampers, it becomes possible to use the stability-improving characteristics of the bar without sacrificing any appreciable loss of control. Thus, the stabilizer bar becomes one of the most successful methods of increasing the stability of a helicopter. Today, when we see a helicopter rise gently from the ground, hover gracefully for a moment, then move off easily in directional natural. But it was not always so simple. The early designers of helicopters encountered many difficulties before they were able to get one of their craft off the ground. And they had still more difficulties to overcome before they were able to control its flight. One of their major problems was dissymmetry of lift, which means simply that in directional flight, rotor blades always tend to exert more lift during the advancing half of their cycle of rotation than they do during the retreating half. The result, of course, is an unfortunate tendency for a helicopter to turn over on its back. The cause of dissymmetry of lift is fairly simple. Lift, as we know, is produced by the passage of air over an airfoil. The air passing under the airfoil is compressed, forming a high-pressure area. The air passing over is accelerated, forming a semi-vacuum, or low-pressure area. This results in the creation of the force called lift. The faster the air passes over the airfoil, the greater is the lift produced. All other factors being equal, lift will vary as the square of the velocity. In a helicopter, of course, the rotor blades act as airfoils to produce lift. And the faster the air passes over the blades, the greater is the lift which is produced. Now suppose the rotor of our helicopter is revolving so that the tips of the blades are traveling at a speed of 350 knots. During vertical flight, of course, the blades will produce the same amount of lift at all times, since the air will pass over them at the same speed during their entire cycle of rotation. But the moment the helicopter starts to move in any direction horizontally, a dissymmetry of lift is produced. That is, the blade advancing through the unshaded area will begin to produce more lift than the blade retreating through the shaded area. If the helicopter is moving forward at 50 knots, then the tip of the advancing blade will be moving through the air at 350 plus 50, or 400 knots. Likewise, the retreating blade will be moving through the air at 350 minus 50, or 300 knots. Since the lift produced by an airfoil varies as the square of the velocity, it is apparent that the lift produced by the advancing blade is considerably greater than that produced by the retreating blade. And this dissymmetry of lift, if nothing were done to counteract it, would soon result in the helicopter turning over on its back. In order to prevent this from happening, some means must be employed which will permit the advancing blade and the retreating blade to produce equal amounts of lift. In most modern helicopters, this is accomplished by flapping. The advancing blade is allowed to flap up, while the retreating blade is allowed to flap down without changing pitch angle. If the advancing blade were not allowed to flap up, it would follow this path, and the relative wind would be from this direction. However, when the advancing blade is allowed to flap up at a high angular velocity, there is a change in the direction of the relative wind. This new path taken by the blade through the air results in a smaller angle of attack. A smaller angle of attack results in a reduction of the amount of lift. Thus, simply by allowing the advancing blade to flap up, we reduce the amount of lift which it produces. It is this difference in the relative wind caused by the flapping action which reduces the amount of lift. Meanwhile, on the other side of the helicopter, we increase the amount of lift produced by the retreating blade. Let's see how that is done. If the retreating blade were not allowed to flap down, this would be its path, and the relative wind would be from this direction. The relative wind is always opposite to the rotational path of the blade. Now, as the retreating blade is allowed to flap down, there is a change in the direction of relative wind, which results in a larger angle of attack. It is this difference in the relative wind, caused by the flapping action, which increases the amount of lift. Thus, by decreasing the amount of lift produced by the advancing blade and increasing the amount produced by the retreating blade, the two sides are brought into equilibrium. In fully articulated rotor systems, freedom to flap is made possible by a hinge near the root of each rotor blade. In the semi-rigid type of rotor system, freedom to flap is made possible by the teeter-totter action of the rotor head. As one blade flaps up, the other flaps down. Since the forces involved cause one blade to rise by an amount equal to the fall of the other, the seesaw mount or semi-rigid rotor construction poses no problem. No matter which mechanical means is used to permit the flapping action, the blades will follow the same path and produce the same result, an equalization of lift. Now, by the use of the cyclic control, the pilot can vary the amount of lift produced by the advancing and retreating blades, and can change the attitude of the rotor disc at will. By changing the attitude of the disc, he can maintain the desired attitude of the helicopter. Dissymmetry of lift, then, is prevented by changing the angle of attack of the rotor blades to equalize the lift produced. And it is only when this has been accomplished that a helicopter is able to fly with stability in directional flight. Do you ever wonder why a bird is able to fly long distances without flapping his wings? It's because he knows his aerodynamics. He knows instinctively how to locate an updraft and may soar for hours by making efficient use of aerodynamic forces. He knows that in order to gain altitude or soar in a given direction, he must have a suitable angle of attack, even though his attitude remains in an almost constant nose-down or beak-down position. However, man wasn't born with built-in flight instincts, nor did his mother teach him aerodynamics. Since that part of your education was neglected, we'll try to supply it in part. First of all, it is necessary to understand the factors which give you lift. In general terms, lift equals angle of attack times density of the air times area of the wings times velocity of the airfoil through the relative wind. Of the four factors which give you lift, the pilot can control only two: angle of attack and velocity of the airfoil. In a helicopter, the velocity of the airfoil results basically from the rotation of the rotor blades. A rotor blade is a wing or airfoil which flies in a circle, thus the term rotary wing. The chief characteristic of rotary wing flight is that relative wind and resultant lift is created by the rotation of airfoils through the air. In other words, the rotary wing performs the same function for a helicopter as a fixed wing for an airplane. The only difference is that in order to produce lift, a rotary wing flies in a circle, whereas a fixed wing moves forward through the air. Whether a helicopter is in flight or at a hover, the pilot maintains a constant rotor RPM. Therefore, the way he varies lift is to vary angle of attack. To understand lift fully, however, you must understand not only angle of attack, but also angle of incidence, which is sometimes called pitch angle. On a fixed-wing aircraft, the angle of incidence is determined by the relative position of the fuselage and the wing. The angle formed by the longitudinal axis of the aircraft and the chord line of the wing is the angle of incidence. The chord line of a wing is an imaginary straight line extending from the leading edge to the trailing edge. For our purposes, it is used to measure angles in reference to the wing. On a fixed-wing aircraft, the angle of incidence cannot be changed by the pilot. This leads us to the one essential difference between angle of incidence on a fixed-wing aircraft and on a helicopter. We can see this difference by observing non-rotating blades. In a helicopter, increase or decrease the angle of incidence either by moving the collective pitch control or by moving the cyclic control. Now let's take a closer look at rotor blade angle of incidence. In broad terms, a rotor blade's angle of incidence is the angle between a reference line of the helicopter and the chord line of the rotor blade. Remember that rotor blade angle of incidence may be increased or decreased by the pilot. A variable angle of incidence has a single but extremely important function. It enables the pilot to control his angle of attack, and angle of attack is one of the most important determining factors in producing lift. Angle of attack is the angle between the chord line of the airfoil and the relative wind. To understand relative wind, let's assume that these dots represent particles of air which are not in motion. However, when an airfoil passes through them, a relative motion is produced. This relative motion is commonly termed relative wind. Since this air motion is entirely dependent on the movement of the airfoil, it will always be directly opposite to the direction in which the airfoil is moving. Thus, if the airfoil moves in this direction, the relative wind will be directly opposite. When the airfoil moves in a different direction, the relative wind will also change. Remember that the relative wind is always directly opposite to the movement. Now let's take a look at the similarities between a fixed wing and a rotor blade. Their angle of attack is measured in exactly the same way. On both, it is the angle between the relative wind and the chord line of the airfoil. A small angle of attack results in a small amount of lift. If the angle of attack is increased, the amount of lift increases. The greater the angle of attack, the greater the lift. However, there is a limit to this. At angles greater than about 15 degrees, there is a tendency to stall, and this results in a sharp reduction in lift. As we pointed out earlier, a helicopter pilot varies his lift and achieves control of the helicopter not by varying the RPM of the rotor, but by varying the angle of attack of the rotor blades. By applying collective pitch, he changes the angle of attack equally on all main rotor blades in all positions. Through cyclic control, however, he can increase the angle of attack on one half of the rotor disc and simultaneously decrease it on the opposite half. When this happens in flight, the rotor disc is made to tilt, and the helicopter moves off in the direction in which the disc is tilted. This results in a change of attitude in the helicopter. The aircraft tilts in the same direction as the disc is tilted. Attitude is the angle of the entire aircraft relative to the horizon. This nose-down attitude is characteristic of a helicopter in forward flight. The faster the flight, the lower will be the nose. Stopping quickly results in a change of attitude. This nose high altitude is characteristic of a sudden stop. Lateral motion also changes the attitude of the helicopter. Here, as always, its attitude tilts in the direction of flight. Attitude, then, is the angle of the entire aircraft in relation to the horizon, and it should never be confused with angle of attack. Now let's review some of the more important points of this film. Of the four factors which give you lift, a helicopter pilot can control only two: the angle of attack and the velocity of the airfoil. Since rotor RPM is kept constant, the only way to vary lift is to vary angle of attack. Lift holds you up and also provides horizontal and vertical control. A helicopter's rotor blades perform the same function as an airplane's wings, except that they provide both lift and thrust by rotation. In broad terms, the angle between a reference line of the helicopter and the chord line of the airfoil is called the rotor blade's angle of incidence. A variable angle of incidence enables a pilot to vary his angle of attack. Angle of attack is the angle between the relative wind and the chord line of the airfoil. There are two ways to vary angle of attack. Applying collective pitch changes it equally on all main rotor blades in all positions. By applying cyclic control, lift is increased on one half of the rotor disc, decreased on the other half, and the disc itself is tilted. The helicopter will fly in whatever direction it is tilted. This, of course, results in a change of attitude of the aircraft. The helicopter is capable of many maneuvers once deemed impossible in an aircraft. Knowledge of your rotor blade angles is a solid foundation on which to build a full understanding of the principles of helicopter flight.